So we continue. I will continue to talk about Ludwig von Bertalanffy book on general system theory. And this part is actually also important following the first part where I talked about the philosophy and the three main aspects that Ludwig has identified when it comes to his theory, that is paradigm shifting, or shifted paradigm in scientific thinking away from classical science into something new that he called general system theory. So now I will talk more about the approaches that Ludwig identified at the time from his book in the 1960s, which is something that is really useful to keep an eye on and to kind of have a read if you get a hold of the book. And the part that I'm talking about in the book is from page 15 up to 28. So to start with, Ludwig talks about and mentions Kuhn about having a scientific revolution. So he references Kuhn in terms of how Kuhn defined a scientific revolution by the appearance of a new conceptual schemes or paradigms, which Ludwig, he thought general system theory would fit within this new conceptual scheme or paradigm that Kuhn was talking about. And as part of this new conceptual scheme or paradigm, there is an emphasis on philosophical analysis. And also part of that is to have some sort of analytical approach. And then Ludwig starts talking about analytical approaches in classical sciences and how this compares with the analytical approaches that he identified for general system theory, to make that point of differentiation about why general system theory is a new paradigm. So just to give you some background about what he talked about in here, which is actually very useful. He says that the criteria that Kuhn identified from a study of the classical revolutions in physics and chemistry, they represent excellent description of the changes brought about by organismic and systems concepts and elucidate both their merits and limitations. Especially, and not surprisingly, systems theory consists of a number of approaches different in style and different in aims. So, to him, analytical procedure that comes under the classical sciences is different. It means that an entity investigated is to be resolved into and hence can be constituted or reconstituted from the parts put together. That is any parts, any elements put together. These procedures being understood both in their material and conceptual sense. So again, this is important to realize it's not just something physical, it's also something conceptual and abstract. This is what Ludwig thinks as the basic principle of classical science, or what merits us to say this is classical science, which can be described in different ways. And then application of then Ludwig goes on to talk about the application of the analytical procedure and how it depends on two conditions. So you need to fulfill two conditions for science to be classified as classical based on Ludwig's point of view. So the first condition is that interactions between parts be non-existent or weak enough to be neglected for certain research purposes. Only under this condition can parts be worked out. And he puts this between brackets. Actually, logically and mathematically, and then be put together. The second condition is that the relations describing the behavior of parts be linear. Only then is the condition of summativity, of summation given, i.e., an equation describing the behavior of the total is of the same form as the equations describing the behavior of the parts. Partial processes can be superimposed to obtain the total processes, and so on. So this is a really, really useful way that Ludwig described the two conditions that make analytical procedures under classical science would need to fulfill to be classified as that. And these are written under pages 16 and 17 of his book. But these, he argues, so this is when he relates that back to his argument about why general system theory is a new paradigm and a new science, is because these conditions, these two conditions that I just mentioned, about the interactions between parts and also the relations that, when we talk about describing relationships between parts, that has to be linear. These are not fulfilled really when it comes to, and do not apply to entities when it comes to systems, when it comes to studying systems, i.e. consisting of parts in interaction. Okay? So this is his argument, because things are interacting, and this makes it really hard to go about studying systems the same way as classical science would do, in linear ways, and by putting parts together, basically. And to talk about that, to talk about as I mentioned in the previous video, video that I did, is to have a new science, you need a new analytical approaches, basically. This is what Ludwig is arguing. And as part of this section of the book, he lays out mathematical and conceptual or verbal or non-mathematical approaches that could be used and were used at the time when Ludwig wrote this book. So he mentions few of these, starting from mathematical models or approaches that were being applied to different systems, and then he goes on to talk about the verbal ones. So I will mention some of these and talk a bit quickly about them, just to give you an idea, and you can feel free to jump in and read the book, which I highly recommend, because he goes into every single one. And it is a nice way of giving you some background about the different approaches, the history probably of of some of the approaches that we've heard of, like cybernetics and game theory and all that. So if you're interested, feel free to go ahead and read those from pages 17 of his book. So starting with mathematically based analytical approaches that Ludwig talked about, the first one that he talked about was classical system theory, which applies classical mathematics, as it suggests, i.e. it applies calculus. Okay, and the aim of this one, Ludwig says, is to state principles which apply to systems in general or defined subclasses, like, for example, closed and open systems. The second type that he talked about, the second type mathematical model or approach that he mentioned was computerization and simulation. And these are sets of simultaneous differential equations as a way to model or define a system, or if linear, to solve even in the case of a few variables. Okay, if nonlinear, they are unsolvable except in special cases. And then the third type that he gives is called compartment theory. So compartment theory is an aspect of systems which may be listed separately because of the high sophistication reached in the field of compartment theory. And here he gives the example of the system consisting of subunits with certain boundary conditions between which transport processes take place. Another type that he gave of analytical approach was set theory. and this is the general formal properties of systems, closed and open systems, can be axiomatized in terms of set theory. Graph theory is also another approach that Ludwig talked about. It's about many systems problems that concern structural or topological properties of systems rather than quantitative relations. Net theory, he also talked about net theory, which is included in the book. And this is connected with set, graph, compartment, etc. theories, and is applied to such systems as nervous networks. Cybernetics is a big one that he talked about, which is a theory of control systems based on communication. So it's based on transfer of information between system and environment, and within the system and control, between brackets, feedback of the system's function in regard to the environment. Okay. And information theory is another type. And it's based on the concept of information defined by an expression isometric to negative entropy of thermodynamics. And he also talked about the theory of automata as another approach, which is the theory of abstract automata with input, output, possibly trial and error and learning. And he gave the example, a beautiful example in here, which is the model that is used in the Turing machine as an example of theory of automata. And he also talked about other approaches, such as game theory, decision theory, queuing theory, as also other examples of mathematical approaches that could be used for general systems theory. But then also he makes a very interesting, argument and a discussion point. He says that in homogeneous and incomplete as it is, confounding models such as open system, feedback circuit with mathematical techniques, like for example, set, graph, game theory, etc., like the ones that I just mentioned, and the ones that he talked about, such an enumeration, he argues, is apt to show that there is an array of approaches to investigate systems, including powerful mathematical methods. To the point to be reiterated is that problems previously not envisaged, not manageable, or considered as being beyond science or purely philosophical are progressively being explored, thanks to these mathematical models. However, he also argues that there are fundamental problems for which no mathematical techniques could be available, something that I also I feel strongly about. So disappointment of overextended expectations has occurred with these mathematical models. And he gives examples about some of these disappointments when it came to cybernetics as an example of the shortcomings of some of these mathematical models. And in some cases, they might not be shortcomings. They're there designed to serve a certain purpose, to look into certain systems, right? So he then suggests something. The advantages of mathematical models, the unambiguity, possibility of strict, deduction, verifiability by observed data are well known. So these are the advantages of using mathematical models, and I would argue also they are advantages of quantitative research techniques in general. But this does not mean that these models formulated in ordinary language are to be despised or refused. So this is where Ludwig makes the argument of non-mathematical models as well, and the usefulness of these. And he gives example of an analytical approach that could be used for with his general system theory is, he called it a verbal model. And he said that a verbal model is better than no model at all, or a model which, because it can be formulated mathematically, is forcibly imposed upon the falsities of reality, which is, I thought, is really a beautiful way of explaining the limitations of mathematical modeling sometimes. And those who ascribe, or those who think very rigidly about data and nothing else. And he says also that theories of enormous influence, such as psychoanalysis, were unmathematical, or like the theory of selection, their impact far exceeded mathematical constructions, which came only later. And then he goes on to give a really, really excellent a paragraph on page 22, which I really liked. Mathematics essentially means the existence of an algorithm, which is much more precise than that of ordinary language. History of science attests that expression in ordinary language often preceded mathematical formulation, i.e., invention of an algorithm. Examples come easily to mind: the evolution from counting in words to Roman numerals, to Arabic notation with position value, equations from verbal formulation to rudimentary symbolisms handled with virtuosity by others. Theories like those of Darwin or of economics, which only later found a partial mathematical formulation. It may be preferable first to have some non-mathematical model, Ludwig argues, with its shortcomings, but expressing some previously unnoticed aspect, hoping for future development of a suitable algorithm, than to start with premature mathematical models following known algorithms and therefore possibly restricting the field of vision. And I really like this paragraph. It is something that I've used in my PhD and my research, where I didn't go with quantitative research. When I looked at my phenomena from a systems thinking point of view, I went with qualitative research, and I did not go with a certain model that is mathematically based, that is off the shelf, that is out there. And I started with something that has not been, but I started with something that hasn't been done before. And I liked what Ludwig said from the 1960s, that is, to justify why sometimes mathematical models could be done later or might not be useful with certain phenomena, or if we want to examine certain models. They might not be the only answer, or they could be limited. So it's something to keep in mind. It's something that I really, really liked that Ludwig mentioned under page 22. So models, he argues, in ordinary language, therefore, have their place in system theory. The system idea retains its value even where it cannot be formulated mathematically, or remains a guiding idea rather than being a mathematical construct. And he gives further examples to make this to explain this argument. And something that is actually also useful to think about is that he also, before closing this section in his book, he actually mentioned the role of hierarchies in systems in general. And under table 1.2 on page 26, he gives an informal survey of main levels in the hierarchy of systems. So he develops some sort of a hierarchy of the systems that we see around us to give you an idea about how he thought about hierarchies within systems. So he starts from static structures as a level, all the way to clockworks, control mechanisms, open systems, lower organisms, animals, man, which is humans, to socio-cultural systems and then symbolic systems. And he describes every single level and give examples of these. And then he touches on if there are any theories or models that would help approach or do an analytical approach for each of these systems. For example, with humans, with man, as he called it, with that level, his description was that there is symbolism, there is past and future, there is self and world, there is self-awareness, as consequences, communication by language as examples and description of this level. And then in terms of the theory and models on how to approach humans, he mentioned the incipient theory of symbolism. And then in terms of another example on sociocultural systems, he describes them as populations of organisms, human included. And he gives examples of these as being symbol-determined communities, cultures, and man only. And in terms of the theory and models that he used, he mentions statistical and dynamic laws in population dynamics, sociology, economics, possibly history, and beginnings of a theory of cultural systems. So he finishes that chapter by saying that there are many system models out there, more or less progressed. Some of them are elaborate. Certain concepts, models, and principles of general systems theory, such as hierarchic order, progressive differentiation, feedback, systems, characteristics defined by set and graph theory, etc., are applicable broadly to material, psychological, and sociocultural systems. Others, such as open system, defined by the exchange of matter, are limited to certain subclasses. As practice in applied systems analysis shows, diverse systems models will have to be applied according to the nature of the case and operational criteria. So this is a very nice way to end this chapter.